Good afternoon. I'm going to present my work titled Monitoring Bridge Performance Under Vehicle Loading with Dynamic Fiber Optic Strength Sensing. So the objectives of this work is study service load performance assessment of a reinforced concrete bridge. The objective is collect and analyze strain data efficiently from the bridge, characterize load distribution across the bridge structure, and develop and validate computational models for performance analysis. We are currently in this stage of the project, and the long-term objectives are evaluate long-term bridge monitoring using the dynamic fiber optic strain sensing, and also use this data for post-earthquake damage evaluation. So the case of the study is this bridge. I'm going to mention more details about that a little bit later, but just to mention that it's instrumented with fiber optics. So that is why I want to start with a little background about the type of fiber optic that we are using there. For use fiber optic, there is these different technologies. One of them use an interrogator that launch a light pulse to the fiber optic cable, and we can use the light loss in that cable as a measure of different phenomena that is happening to the fiber. One of these phenomena that happen to the fiber is backscattering. Backscattering occurs when the light is reflected to the original source. So this light is sent to the cable using this interrogator, and then this light is coming back to the same interrogator, and that changes in the backscattering that depend on the property of the cable is that allow us to measure, for example, strain changes or temperature changes in the fiber optic. There is three types of backscattering way to measure the wavelengths. There is the Rayleigh scattering, backscattering, the Raman backscattering, and the Brioin backscattering. The one that we are using in the bridge is the Rayleigh backscattering that can measure strain and temperature. There is two main approaches to use that. One is optical time domain reflectometry, or OTDR, that measures variation in the signal amplitude over time. That allows to measure several kilometers of fiber, but with lower resolution. The other type of technology is optical frequency domain reflectometry, or OFDR, that measures phase shift in the fiber optic and offer a higher spatial resolution. We're talking about sub-millimeter resolution, and is able to measure dynamic measurement over shorter distance, about 100 meters, or the one that we are using is 50 meters, which is for a structure something that we can use. The advantage of optical frequency domain reflectometry is that offer this exceptional spatial resolution. So it's very useful to measure, for example, local behavior such as crack in concrete. These cracks can be measured depending on the type of fiber that you're using. For example, if the coating of the fiber is too thick, we are not going to be able to measure the peaks of the crack with so many details. But if the coating is too thin, we are risking to break, or when we are working with the fiber, not be able to properly work with them. So we need to find some fiber that has enough coating or protection that allows us to measure these cracks. For example, here is the work done by Liu et al. Here at UC Berkeley. And you can see there is some peaks that are showing in the fiber optics that are inside an element that is subject to tension test. So you can compare that to the digital imaging correlation that is shown in the bottom. So it's a direct correlation between the surface crack that we are seeing in the imaging correlation and the peaks that we are seeing in the fiber that are occurring inside this element. So that is the motivation to evaluate the use of this type of technology in a real structure and study the performance. So the bridge that we are studying in the Centennial Viaduct is a bridge that is located in the east side of Berkeley. It's very near to the campus, in going to Lawrence Hall of Science. There is a plan view of the bridge. In the middle part of them, we can see the longitudinal cables that are installed there. There are 4 longitudinal, and there are also 4 transversal, as you can see in this plan view of the bridge. This is the middle span of the bridge, and the cables are in the first half. So here are some images of the cables inside the construction when the bridge were construction. So you can see that the cables are in the same direction as some rebars and before the pouring process of the concrete. Some of the key advantage of this distributed fiber optic sensing is that it's lightweight and compact, so it doesn't affect the concrete. It's also not corrosive and immune to electromagnetic interference. Also is suitable for harsh environment, such as the pouring of concrete, for example, can survive that without issues. Actually, the more critical part is when the construction is happening, because there could happen some issues that you can broke some cables, but after the cables survive the construction, they are very safe inside the concrete matrix. Also, there are some cables in the column, one of the columns of the bridge. This is going to be very useful to detect axial and bending deformation, and is going to be used for post-earthquake damage evaluation, the behavior of the column. There are some images of the installation of those cables. It's very interesting that those cables can survive the harshness of the site, so it's a very nice material. Here is the data collection. In this image, you can see the interrogator are all the setup to go to the site and measure what is happening inside the bridge. There is a photo of some of the members of the research group that has been working with me in the recollection of the data. So I'm gonna thank all of them that I'll have been helping me, because collecting data on site, there has some difficulties with the dirt in the air, moving equipment, calibration. So I'm very thankful for the help that they has given to the project. Here is a video. Okay, there you go. There is one of the subjects of the study is a track that, a shuttle that maybe some of you can recognize, is the Bird Transit that pass over that road, which is an advantage for us because we know that we have a reliable vehicle that is going to pass very often, so that is very useful. And all the data that I'm going to show is some of those shuttles. So here is an example of a measure direct from the interrogator reading. So you can see here when the shuttle pass, we have those type of reading. This is one of the longitudinal cables that are on site. And to compare that data, we are using first a very simple model to have a sense of the order of magnitude of the strain that we are going to measure. So we know the shuttle. We have an approximate characteristic of this vehicle. We know that pass over the hill line, the H line, which is from UC Botanical Garden to Lawrence Hall of Science. And between 7 a.m. to 7 p.m., every 30 minutes we have at least one of these vehicles. The road is very busy. There is other vehicles that pass there, but it's good to have like a big one that is happening regularly. For the simple model, we are using a lot of simplification just to, in this stage. The idea is to, as we advance in the project, we are going to use more detailed models, but for the moment we are using a very simplified version of the bridge. And we have here a measurement of the longitudinal cables. This is when the shuttle is passing downward the road, is passing in this direction. So I'm showing these cables, which are not in the road that is passing the truck. So it's the indirect reading, but we're able to see that what is happening. So for example, when the shuttle is in the middle of the deck, we can see that we have an approximation of what is the strain of that portion, and we are measuring that with the fiber optics. For example, in the bottom, the blue line, we can see that the strains are in compression, and then we change to tension as we advance in the cable. And in the top cable, we're having the other way around behavior, which is what we expect there. And as the shuttle move further, we have a change of the strain distribution, and we are reading that with very, very small strain values, but we're able to see that even though the track is not passing directly over the fiber optic cable. Here we have another direction. This is the transversal. So there is some cables that are in loop in the deck. So you can see there is some peaks that happen in some moments that are represented when the track pass over that fibers in the deck. So for example, here we have an instant when the shuttle is over this transversal cable, and we can see the wheels over the cables that are happening there. And also we can see other details. For example, in the blue, the bottom fiber, we are seeing those peaks that are the loading that is passing over here because of the weight of the shuttle. As the shuttle moves, we can see that there is a change. Now the second fiber optic is reading the wheel, so we can detect when the vehicles are passing, what are they doing inside the bridge. And as the shuttle moves, we can see how the peaks are changing, and we can measure that. So in summary, for this stage of the project, we are collected and analyzed strain data efficiently. We have characteristic load distribution across the bridge structure, and develop an initial validation for the model strain data. Here is one measurement, for example, is the transversal cable. And in just one cable, we have the data, for example, what is happening in the deck, but also what is happening along the road in the bridge. So we have a lot of information that we can read with this type of technology. And the future work is enhance the computational modeling for improving the accuracy, and also to detect the difference, for example, in the extreme cables with the middle cables. We know that there is some subtle difference effect because of the moving load, so we want to study that. And also implement weight in motion analysis for the bridge, conduct a long-term bridge performance monitoring, and as a final stage, perform post-earthquake structural assessment for the bridge. So, thank you.